Hello everyone, this is Amal. I am a technical support specialist in CFD responsible for the customers in the EMEA region. Today, for our webinar series, we're going to be talking about FluidStructure Interaction in Autodesk CFD. I have with me my colleague Marwan. Hi Marwan.
Hi everyone, hi Amal.
Hi. So just for your information, you're going to be having the slides as well as the files, the support files of CFD or other software that we worked on under the link that you see below on the slide. So today we're going to be introducing you like a small definition of the fluid structure interaction. What is it exactly? Then I'll be demonstrating some of the applications of fluid structure interaction that you can have using Autodesk CFD. I will be sharing some useful content links from our webinars, from some Autodesk University courses, as well as articles, the help documentation of Autodesk, many useful links in here that can help you establish this kind of analysis. Then we will give like a small summary about, or I'm going to talk briefly what are the supported FAA programs that we are having, and then finally in the last point, Marwan is going to specifically talk about how do you take the results from CFD and map them on an FAA model. We're going to see how to do this procedure from the CFD model till the FAA model. Before moving to the next slide, or let's define first what is fluid structure interaction, and then I'll be asking you some questions. So what is a fluid structure interaction? So in general, defined by Wikipedia, is the interaction of some movable or deformable structure with an internal or surrounding fluid flow. And these fluid interactions can be stable or oscillatory. So we can assume, for example, a cylinder inside a water pipe can be treated as a fluid structure interaction, or for example, you have a valve submerged into a pipe, and where fluid is surrounding it from all the directions, and where you can analyze the fluid structure or the interaction of the fluids on the valve. So now I'm going to ask you two questions regarding the fluid structure interaction analysis. I want to know if you ever use fluid structure interaction in your daily work, or in some of the projects you're working on. Yeah, just to see how many people are interested here in seeing how to set up a fluid structure interaction, and how, especially to map the results from CFD to FAA programs. So I can see that there are a lot of people participating. So
Looks like everyone answered.
yeah.
Right.
So now we can collect the responses. So I'm just seeing how we can pull the results. Can you see it, Marwan, with me also on the screen?
I think you have to click the share button next to the first question.
Oh yeah, this is true.
There you go.
Exactly, cool. So we have we use fluid structure analysis, we have 58%, and 42% with no, we don't use fluid structure interaction. This is cool as we have here more than the half who are experts or are usually using this type of analysis, and then a bunch of people who are interested in learning more about this type of analysis. So next and last question. So which structure analysis package do you use usually? Autodesk Simulation Mechanical, Autodesk Nestran, ANSYS, or others? We're going to give you more seconds to answer, and then we can pull the results. Okay, cool. Thanks for voting. So let's see the results together. So we see that there is 47% for people who are using Autodesk Simulation Mechanical, 12% using Autodesk Nestran, 12% using ANSYS, and others for the remaining of the people, which is really cool as we see a lot of people who are sticking to Autodesk products. Thanks for sharing your responses. So now we will move together to see some of the fluid structure interaction applications in Autodesk CFD. So they mainly include wind loading analysis. It depends on what you want to simulate. It's either a wind turbine simulation. You want to see the stresses over the blades of the wind turbine, or if you are having a load over a whole building, so you want to see the loads over the building, collect the pressure results in CFD, and then transfer them into an FAA program, or even like a simple tower, and you want to simulate to run it into CFD with an airbox and see the pressure loads over the structure, and then transfer the results and see the stresses as well as the deformation that may happen over the structure. A second application is the flow control. It may be a pipe, for example, on the left side picture, where you have a pipe and then flowing fluid, and you have kind of flexible body that moves with the as the fluid flows. So this is kind of a fluid structure analysis where you want to see how the fluid flow affects the motion of the flexible or its deformation. And then there is also the case of a pump or a turbine where you have a moving body or blades. And you want to see when these blades move, how they will interact with the fluid. You want to see the pressure profile over the blades. That can give you an idea about the stresses put on the blades. The third application can be also water, as I already mentioned, a pipe full of water with a valve inside it, semi-opened, and you want to see the stresses over this valve. So there are a lot of or different applications of flow control. They are just simple examples. You can find more in CFD. So the third application is the water transport and infrastructures. Some examples are the flow of water from a dam application, for example. So you want to see how the water flow, how it interacts with the structure of the dam. We have also the interaction of a free surface or a sloshing application in a model, or for a case where you have a filling body, so you want to see how when the fluid flows, how this flow or jet will impact the solid just below it, or it depends, or in front of it. So we seen a lot of applications that we can use for fluid structure analysis in Autodesk CFD. I wanted here to share with you some useful content from our knowledge database. So I sum up all the articles, or the interesting articles that I found on our AKN, useful help from our help documentation on how to proceed, all the different steps, how to transfer the results from CFD into FAA program, and then some videos. So regarding the articles, you can find articles treating how to solve common problems that you may have while transferring CFD results into FAA programs. Or when you are importing a file, a Nastran file, for example, and you're facing some unit problem. So here's some solution how to solve this. And then here I have shared some links of some common models of the fluid structure interaction, for example, the vortex shedding models, or even there is an application, or we have also the webinar about simulating an ACA airfoil, and how the fluid interacts with the wall just of the airfoil. So we have a rich library concerning this topic, and our goal right now is to make it larger in order to allow access for you for more knowledge. So regarding the supported FAA programs, we have a good library, like you can use Nastran, CAD, ANSYS. We have many supported FAA. We have a whole list that you can find in our in a published article in our knowledge database. So Marwan, so after introducing the analysis of the fluid structure interaction, we're going to move to a demonstration section where Marwan will be showing to you how or explaining, especially this the help documentation article, the steps how to go from the CFD analysis or results, and go to or transfer or map the results on an FAA model, the same model for sure. So Marwan, do you want to
go ahead,
proceed to the
sure.
demonstration?
Yeah, if you can go ahead and make me the presenter here.
Exactly.
And I will share my screen.
Are you sure you want to make? Yes. So you have the ball.
All right, so screen. All right, let me know if you can see my screen here. And
yeah, I can see it.
All right. Thank you, Emil, first of all, for the introduction and the useful information. One thing I wanted to add to what Emil said is that if running a model in just inside of CFD, of course, inherently has fluid-to-structure interaction because the fluid is bound by a structure, but that structure is considered to be rigid. You know, we can calculate, you know, let's say in a motion analysis or in a free surface or in any kind of analysis, you know, if you don't have any boundary condition, that's considered to be a wall. So that's interaction between fluid and the structure. But what we are talking about today is taking that interaction and calculating stresses in the solid model. That's what we would be demonstrating here. There's always interaction between fluid and solid, and that happens all the time inside of CFD. But here we're going to take it one step further. We're going to take the pressure, or you can also take temperature output out of CFD and use it in a structural analysis. In our examples today, we're not going to be taking temperatures, we're just taking pressures, but you can do that just the same. It's the same procedure, except that if you do run and solve for temperatures inside of CFD, you can also take those results and superimpose them on your structural model to calculate thermal stresses. The first example I have here is, let me just share this slide, is for an internal flow. We have a pipe with some kind of a...
Just a second, Marwan. It's like we're seeing your second screen. Right now we are seeing the file of the PowerPoint. Probably you need to...
Really?
Yeah, to switch the screen.
Hold on.
Okay.
Are you seeing PowerPoint or you're seeing the model?
We are seeing the PowerPoint on
oh yeah,
slide.
I just wanted to show. Yeah, I wanted to show the PowerPoint first. Just.
It's on the introduction right now.
What now?
Yeah.
Yeah, that's what I wanted to show. Just the overall model here is that we have a pipe with a certain obstruction, and we're going to run a fluid flow analysis and calculate the stresses and deflections, maybe more so on that obstruction.
Talking in here about the first, it's the first slide that we see. Probably we can check with the staff if...
Do you see Inventor now?
No.
Interesting.
So we can see how to fix this.
Screen, my screen.
Maybe try to reshare. There you go.
All right. Let's do it clean.
Thanks.
Do you see it now?
Yeah, everything is perfect now. Thanks.
All right. Thank you. All right. So what we have here is really a simple model. We have a pipe. We have a fluid. I also modeled the fluid inside of an Inventor. And if I turn the visibility off for this fluid, you can see what's inside of it, which is the piece we're interested in calculating the deflection of, that little obstruction inside. That's where the interaction is going on, and we want to calculate the stress on that. So the first step would be to open this model inside of CFD, as we see here. I already ran it, actually. It's really a simple model, simple setup. It doesn't really matter what the materials are. Of course, the fluid material does matter, because depending on what fluid you have, it's going to affect your reaction forces and the pressures inside. What we have for boundary conditions is a certain flow rate of 100 gallons per minute. So that's our inlet over here. The outlet, of course, is the other side, where we have a zero pressure boundary condition specified, and the rest is pretty simple. The fluid is water, and the pipe and the obstruction inside, I set the material to ABS molded, and I set the analysis to run. And this is what we have here. Let me just change this just to show you the cut plane here of the flow. So you got, of course, accelerated flow down here because of the obstruction, and that calculates our pressures, which we are going to use in our FEA model. So back in Inventor, I'm going to, let me show this again. I'm going to go to environments. I'm going to be using Nastran NCAD for this model. And actually, I'm going to also show you how to do it in simulation mechanical. So let's first show it in Nastran NCAD. So we go to environments, Autodesk Nastran NCAD. Go down to materials. I'm going to set the materials here to aluminum. You can choose any material that you want. The fluid, I'm going to deactivate actually. So the fluid part, which is this part here, I'm going to right click and exclude from the analysis. I'm going to generate the mesh here, see what we get. It's probably a bit too coarse. So I'm going to go in and refine the mesh. And there's more than one way to refine it. You can refine each part individually by going to a table. Let's do that here. Part 1 pipe, let's change that to maybe 0.2 for the pipe and do this for the obstruction and generate the mesh again. And we're going to say that looks, I don't know how well you can see the mesh here. Okay, this is better. I'm going to say that's good. The next thing I want to do is to define the contact between the parts. So I'm going to generate the automatic contact here. And it will detect all the contact between the parts and populate this tree. Of course, since I deactivated the fluid, a lot of these contact pairs are no longer needed. So I'm going to right click and suppress those. Next, I'm going to apply a simple constraint over here and make this fixed. And now the load, which is the most interesting thing here that relates to fluid flow. And for that, I'm going to go down to loads, right click and go to new and change the type to from output and come here and select the output, not the output actually, I changed the file type so it's CFDST and I navigate to where this model is. And this is the file. And the load is not going to be temperature, that's going to be pressure. And I hit OK. Oh, found not found. Actually, this is very interesting that it's saying found not found. Actually, it does that because I still have it open in CFD. I'm going to exit CFD. Sure, we can save it. Nothing changed here. I'm going to hit OK, and now it's not going to complain. Now, of course, this is a simple example. Your model might be more complicated. You might have other loads if you want to, and so on. But for the purposes of this webinar, we're going to say that's good. I'm going to click on Run. Actually, I'm going to, let's go ahead and do that. This might take, due to the following, why not? Nastran file cannot be created to the following details. Geometry not applied. Huh. Well, let's then open the one that I had already made, which is the same exact setup here. Webinar. Make the environment. Oh, it didn't work either for some reason. Let's try it again. Should have worked. Oh, wait, did I not? Yeah. Well, let's try this again here real quick. All right. Sorry about that. That's what happens when you work with the model. So many different variations. It
seems
starts
that
acting up.
there is a problem in the mesh, isn't it, Marwan?
Yeah. Let's do this fluid, exclude it, edit, and say 0.15, generate the mesh. Here we go. Okay, and let's generate the contacts.
So what was exactly the error at the beginning? Because you did change the size of the mesh, isn't it?
Yeah.
So just to explain.
Yeah, let's do that again. Let's suppress these guys. Let's add a constraint here. Let's add the load again. That's again going to be from file. And the file type is going to be CFDST. Go here. And change that to pressure. And let's try this again. Yeah, could have been the mesh. I don't know why it complained about it, but hey, you got a second chance to see it again. In case we missed something.
Yeah, this is nice.
Yeah, so it's going to generate, yeah.
At least we went through all the steps that you've made and checked everything from the beginning. So now we don't have any errors anymore.
Yeah, and really importing the results is just as simple as selecting the CFD-ST file. And that's going to automatically import the results from your CFD analysis. Actually, while this is running, I can show you how we do that in simulation mechanical. Since 47% of you use simulation mechanical, I'm going to go ahead and do the, it's a little different, but it's pretty much the same idea. So I'm going to open the Inventor Assembly and simulation mechanical here. That's example 1. Put this out of the way, maybe. Static stress. That's part 2 is the fluid. We're going to suppress that mesh.
So here you're doing the same task but with another software, isn't it?
That is correct. We're doing the same thing. Exactly. And we're going to set the material for both to aluminum as well. T6. And actually this is done. So let's take a look. And we can see that we have a point of high stress here. And if we look at the displacement, of course, the maximum is going to be here. Oops, like this. Which is what we would expect out of this. Again, I didn't apply any other loads. The only loads are those that came in from CFD. Now, back in simulation mechanical, it's again pretty much the same thing. I'm going to select the surface here, right-click, and add general surface constraint, and that's going to be fixed. The loads are going to be specified in the analysis parameters. There's a special tab here for fluid reactions from CFD. So very similar to what we just saw in Nastran and CAD. Let's go to the proper folder here. Oh, nope. All right, here, this, and open. And it populates it. If there's more than one scenario or one design, you can choose which one you want, obviously. The one thing to keep in mind is you want to go to multipliers and set the fluid reaction multiplier to 1 or any other number other than 0. And that's all you need to do. Go to analysis, and we would run the simulation.
So Marwan, short question or probably a brief explanation to the attendees. So in CFD, you run a pipe with a fluid inside it, where you defined at the inlet a velocity or a mass flow rate, and then on the outlet a pressure equal to 0. Is that right?
That's correct.
So it's a simple analysis that you run in CFD. Probably it would be good if you just demonstrate how you, or which tool you use to take or to get the results from CFD in order to then input them into sim mechanical or Nastran running CAD.
Yeah, I mean, that was, since we are in sim mechanical, okay, that's the displacement here, which I think matches closely. You know, the different meshes, the results are going to be naturally a little different, but we got 0.017 inches here, and in Nastran in CAD we got 0.015. It's a different mesh. So in simulation mechanical, to import, basically, if you want to use the word import, to import the results or the loads, whichever way you think of it, from CFD, we go to Setup, Analysis Parameters. We go to the Fluid Interaction or Fluid Reactions tab, and we select the CFD-ST file over here. And we also set a non-zero multiplier over in the multipliers table. So those of you who use simulation mechanical are familiar with the multipliers table and what that multiplier does. But basically it multiplies the loads. That's all we needed to do here in simulation mechanical. It's all done in the analysis parameters dialog. In Nastran in CAD, that is done by defining a new load. So we right click here, we go to new, and then we'll just edit this one. You set the load type to from output, then the same thing. You select the CFD-ST file, you get the option to select the design and the scenario, and the load type, which is in this case pressure. And that's all there is to it. Now, of course, if that was an nonlinear analysis, you can probably set the table of multiplier versus time or step. So that's what's involved in importing these results into
I want to add here something very important, that we need to make sure that both of the models, either in CFD or in the FAA program, they have the same location and the same orientation, so that you can map the results without problems.
That's a very good point, Amal. That's right. They have to be the same size and the same orientation. The mesh size doesn't matter because it's going to do a spatial mapping, so it will interpolate for the mesh size. So you don't have to use the same mesh size between the FEA and the fluid model, which is great. But they need to be the same size and the same orientation. Otherwise, I'm not sure what you're going to get. But
and also the units. For example, if you are using a CFD millimeter, so you have to use also an FAA millimeter. Sometimes you forget, for example, or you notice that there is difference in the units, so you need to change it in CFD before running the simulation, because once you run the simulation in CFD, you're not able anymore to change the units. So please make sure that at the beginning of the your analysis or at the beginning of your study, you make sure that the units are both similar in both of the softwares, and to have the model in the same location and with the same size.
Yes, that's right. So the next example is for an external flow, and this is for a stop sign. So that is a stop sign. This is actually a four-part assembly. There's the sign itself, the pole, and two caps that I put on the pole just so that it doesn't generate the internal fluid. Well, actually, it will generate the internal fluid, but this way it's not connected to the external fluid. When you import this into CFD, it will fill because this is not a solid pole. If I hide this, you'll see it's a hollow rectangle for this beam, basically. So this is the model in Nastran, in Inventor. So I built this in Inventor. Let's go and start CFD here. And I'm actually going to open the model that I had already analyzed. So let's go ahead and do that. That's example 2. We sign. This is the model. The interesting thing here is that I generated the external fluid volume right inside of CFD compared to the internal flow, which was generated in Inventor. This outside volume was generated in CFD, and the volume inside the pole here, I suppressed that. We don't need it. So we got our external volume generated in CFD, and the boundary conditions is we have a velocity of 120 miles per hour inspired by the hurricanes we've been getting here in the US. And I don't know if any of you saw, there was a video about a reporter that actually was outside reporting in the weather and got hit by a stop sign. Did anyone of you see it? No.
No, not really.
It's yeah, she was saying, "Oh, don't go outside," and so on. And next thing you know, it's like this stop sign comes flying in and hits her in the face, which is really terrible. Yeah. And I got slip symmetry here on 3 faces, and the pressure of 0 over here. Again, it's a simple setup, and if we go to results, I didn't use the best of meshes. This could have used a little finer mesh maybe, but still, for the purposes of our demonstration, this would be good. So this is our velocity profile, obviously, with the stop sign here blocking the airflow. You're going to get low velocities over here. Back in Nastran InCAD, same basically setup as we used for the first model. So let's go ahead and quickly do that. We don't have to run it. We can open it from the already run model, but we'll go through the setup here real quick. We'll have to obviously mesh the model. I used the mesh size of 2 actually in the model I ran. And same thing, you specify the material. Again, we're going to use aluminum here. As far as a constraint, I'm only going to constrain the base here, fixed in all directions. And again, not to forget our contacts. I generate all the contacts between the parts so that they're all bonded, which is the default. So if I edit any of those, you'll see that it is bonded, which is what I want. Now, if your model is more complex than this, you might want to use surface contact. That depends on what you got. But for this, it's going to be bonded. And again, for the loads, I'm going to right-click on loads, select new, go to the type, and change that to from output. And then look for my file. I'll change that to CFD. You don't want to forget that. The FNO is Nastran output. This is not from Nastran output. This is from CFD. And again, I want the pressure. Okay, found, not found. It doesn't like it when the file is open, it seems. So when I exit CFD, and now when I hit OK, it's not going to complain. I'm not going to run it now. Let me just finish this and save it and close it and open the one that is actually already been run. And that would be this one here. Go to environments, Nastran InCAD, and let's go ahead and load the results. And this would be, I wish it remembers the location, but example 2. Hold on. Oh, here, example 2, sign. Oh, let's use the one from today. Open. Okay, and the displacement is 0.3, almost 0.4 inches is the total displacement. You can go here and show the contour option, deformed option. Okay, that's the actual percent, 10% exaggerated, and that's what it basically would look like. Not quite that much because that's exaggerated, that's not the actual, but that's basically the shape of the deformed stop sign. Now, if you use other FEA packages, the procedure is actually described in the documentation, and what you would have to do is you would have to build your structural model first and then save the input file, be it a CDB if you have ANSYS or NAS if you have Nastran, or the other, those are actually listed in the documentation, the file extensions. In the case of Nastran, it's the NAS file. So you generate your structure, you apply basically dummy loads So you would apply pressure on the stop sign and maybe on the pole here. And then you would run your CFD analysis. And again, these steps are explained in the documentation. You would run your CFD analysis. And then you would basically, once you get your results, you would map them using FEA mapping here under result tasks. FEA mapping, you would select your Nastran or Abacus or ANSYS files and do that, and this will generate a new input file that you can run directly in your FEA package that will have the loads basically plugged in from the output of your CFD analysis.
Interesting.
Yeah. That's basically all I have for today. Do we have any questions?
Thanks, Marwan. So we're gonna see if there is someone or there are some persons who are asking questions. Please feel free to ask your questions about this topic, or if you're concerned about something we talked about, we're just here to listen to you. So we're gonna give more minutes to our attendees to ask questions. If not, so we can wrap this session up. So we get a question, Marwan.
Yeah.
Yeah.
Let's see. Let me
Bunch
look
of them.
at the question.
So,
all right.
How about the use of transient output, and how about using CFD motion module? Are there examples of this?
Yeah, if you have a transient, you would be able to select which set of outputs that you want. So if you have a transient, you're on a transient in CFD, you can request that you want the results to be output every so many steps or just at the end. And as far as fluid-solid interaction in your structural analysis, you would select which set of results you want to use in your analysis. Now, if you are doing also a nonlinear analysis, then you can have a load curve and a multiplier for that set of results. I don't think, let me think, there might be a question, well, can you run a nonlinear structural analysis and read multiple sets of results? I'm not sure you could do that. I would have to look into it, but intuitively I would say no, you're not going to be able to take each set of results from the CFD and read that separately, and you can only read one set of results from CFD and either use it as a static load or you can apply a load curve to it inside of your structural analysis to ramp it up or down or whatever shape you want to give that.
Okay, we have another question. An earlier slide showed a plate being deformed by fluid. Is that possible in CFD? Actually, this deformation is shown only in the FAA program. CFD does only simulate the flow, gives you the results of the pressure exerted on this flexible solid, and then you can see this these results of deformation when you get your CFD-ST file into the FAA program with the pressure loads and see how the deformation will be made by defining the material you're using, for example, let's say a flexible like silicon or something like this, and then see the deformation of the pressure loads.
Yeah, CFD doesn't give you deformation. If you have a motion analysis, it'll give you motion, it'll give you displacements. But that part
exactly
that is displacing is maintaining its original shape. It is not deforming. It's rigid body displacement in CFD. Any solid part in CFD is considered to be rigid and does not change its original shape. It could move if you have motion, it could displace, but it's not going to deform and bend.
Yeah, this is true. So in CFD, it's more about fluid. It's more about analyzing the flow, the heat transfer across solids, but it's not about the structure in itself.
So if you have maybe a rubber part that's going to be bending, it might be an iterative process back and forth between structural and fluid to get the final flow. Because again, CFD can show you that part displacing, but not changing shape. It'll change position.
Okay, let's see if we get more questions. Okay, we're gonna give you 1 more minute and then yeah, we have some active attendees in here.
Can a coupled study be done combining the temperature and pressure output? That is a good question. I have not tested that.
Yeah, it's either we export the thermal results or the pressure results, but I personally never come across having both of them at the same time. And this is a good question, really.
Yeah, that could be an enhancement request actually, because I can see situations where you actually want both. You have the pressure, but also the temperature gradient is significant enough to change, to result in some deformation in your model that you want to, and stresses obviously that you want to look at.
But regarding the file, the input file that you get into Nestor Inkhead on mechanical, sim mechanical, I saw that you have to choose either between pressure or temperature when you demonstrated when importing the input file.
Yeah.
So
now most structural packages, allow you to do temperatures too, so you can get your temperatures straight out of your structural, be it ANSYS or CAD or so on.
If they are coupled or not, both pressure and temperature at the same time. So that was the question. Yeah, we can look into this and send you a response about this. Mm-hmm. Thanks for asking. This is a very good question. Okay, cool.
All right.
Interesting questions, interesting responses. Thanks, Marwan, for demonstrating to us how to import the results. We know you're the experts in the FAA programs of Autodesk. Thank you very much.
My pleasure, and thank you everyone for attending. And please,
And have a great rest of your day. Bye-bye.
And we look forward to seeing you on the next webinar. Bye-bye.